Here we have a particle of mass m on a smooth fixed wedge. There are just two forces acting on this particle. Its weight mg and a force on the particle due to its being in contact with the wedge. So that force is perpendicular to the surface of contact of the particle and the wedge. Okay, let's say that this force has magnitude r. Let's consider the resultant force on this particle. Now the easiest way to do that is to consider the particle in relation to an xy coordinate system, where the x-axis points down the incline and the y-axis is perpendicular to the incline. F is the resultant force on the particle. We could get that by summing these two vectors using the parallelogram law, for example. But let's look at the components of the resultant force. Let's call the x component f sub x and the y component f sub y. So I and j, as usual, are unit vectors, that is vectors of magnitude 1 pointing along the x and y axes respectively. Now we can also note down the acceleration vector. So we can write that in terms of its x component, which I'll call a sub x. That's multiplied by unit vector I, and its y component a sub y. Now Newton's second law tells us that the resultant force F on the particle is the mass of the particle m times its acceleration a. So here's the resultant force, and we need to multiply m by vector a. So when analysing a problem of this type, we can consider the x component of the resultant force. That must equal m times the x component of the acceleration, and similarly the y component of the resultant force is m times the y component of the acceleration. Okay, so now let's get back to this problem. Let's look at the x component of the resultant force on the particle. So we want f sub x. Well, we can see that r has no component in the x direction, whereas the weight does. Let's resolve the weight vector into its x and y components. Well, its x component points down the incline in the direction of the positive x-axis. The y component actually points in the negative y direction. Okay, if we sum these two vectors by the triangle law, we get the weight vector mg. Now this angle in here is also theta. Okay, it's an angle between a pair of lines which are perpendicular to this pair of lines. The side opposite theta is the hypotenuse mg times sine of theta. So this is the x component of mg. So if we want the x component of the resultant force, we add up the x components of the forces that make up the resultant force. So we have mg sine theta is the x component of the weight vector. The x component of r we've seen is already 0. So we just take the x components of the two forces and add them together. And by Newton's second law, that's equal to m times the x component of the acceleration. Okay, so you can see straight away that the x component of the acceleration does not depend on m. The m's cancel out. Now let's look at the y component of the resultant force. To get the y component of a resultant force, we sum the y components of the constituent forces. So there are two forces acting on m. Let's get the y components of them and sum them. Well, what about the y component of r? Well, that's just r itself. It's pointing in the positive y direction. What about the y component of the weight? Well, that's the side adjacent to theta in this right angle triangle. So we multiply the hypotenuse, which is mg, by cos theta. So mg cos theta is a component that's pointing in the negative y direction. So here I'm summing the y components. You know, if you want to, you could write it like this: sigma little f sub y, where little f stands for, little f sub y is the y component of each of the constituent forces, and we sum all those to get big F sub y, the y component of the resultant force. And similarly up here, big F sub x could be written sigma of little f sub x, where little f sub x represents a component of a constituent, the x component of one of the forces, and the sum of all those x components is big F sub x, the x component of the resultant force. Okay, anyway, so here we have the y component of the resultant force. Now we apply Newton's second law. This must equal the mass of the particle, which is m, times the y component of the acceleration. Now, what is a sub y? Well, we actually know what it is from this picture here, from experience. We know that the particle has no acceleration component in the y direction. Okay, in the y direction, its acceleration component ay is 0. So we have r minus mg cos theta equal to 0. M times 0 is 0. So that enables us to find r. So we can see that r is equal to mg cos theta. So the magnitude of that vector is equal to the magnitude of this vector. Now we can write down the resultant force vector. Well, here's the x component, that's mg sine theta. It's multiplied by unit vector I, but the y component is 0. Okay, so here's the y component, and since ay is 0, fy is 0. So we have 0j here, 0j, so we can leave that out. So the resultant force is entirely in the x direction. So the resultant of these two vectors, r and mg, is a vector pointing in the x direction, so it's down the incline. Of course, the acceleration vector points in the same direction as the resultant force, so we could show the acceleration vector here is a, and that's g sine theta. It does not depend on what the mass is. It only depends on the acceleration due to gravity, Earth's gravity, which is 9.81, and theta, the angle of this incline. The bigger theta is, the bigger the value of sine theta is, and hence the bigger the acceleration down this incline. In this problem, we essentially have a fixed wedge. It's not exactly like a fixed wedge, but it's the same idea. Let's indicate the forces on the 6 kilogram mass. Well, we have its weight, 6g, which is vertically down. It's in contact with this surface, so we have a force on it due to the surface, which we'll call r. Okay, so this vector is perpendicular to this surface. Now the string exerts a force on a 6 kilogram mass. Let's say that that force is magnitude t. It's directed away from this mass and along the string. This plane is smooth, so we don't have any friction. Okay, let's look at the 2 kilogram mass. Its weight is 2g, and we know that there's a force on it due to the string pointing away from the string, which also has magnitude t. So it's one piece of string, and we've seen before that the tension is the same throughout that string. Okay, the system is initially at rest. It is released from rest. Let's assume that the 2 kilogram mass moves down with acceleration a. If that's the case, the 6 kilogram mass has to move up this incline with the same acceleration a. Now we don't have to worry about getting these directions wrong, because there's no friction in this problem. You see, if friction came into this problem, we would have to consider a friction force opposing the acceleration of the 6 kilogram mass. And if the system was to move the other way, well, the friction force would be here. So the configuration would be different in both situations if friction was involved in this problem. Friction is not involved in this problem, so the configuration of forces is going to be exactly the same, regardless of the direction of motion of this system. If A comes out to be positive, well, then the chosen direction happens to be correct. If A comes out to be negative, well, we just reverse this direction, and we just take the magnitude of that negative value. Okay, so now let's get the common acceleration. Well, let's look at components of these three forces along this incline. We could say that's our x-axis. Our x-axis is, let's say, pointing up this incline, or we could have it pointing down, it doesn't matter. Well, we'll have it pointing up in this case because we're taking up the incline as positive, because the resultant force or the acceleration is upwards. And let's say this is our y-axis. So to get the resultant force on the 6 kilogram mass, we sum the x components of these three forces. Well, we have plus t upwards, and what do we have down this x axis? Well, we just have to get this component here, the x component of the weight. Well, we use the fact that this angle is 30 degrees. Okay, it's the same as the angle of the incline, as we saw before. And we want the side opposite 30 degrees in this right angle triangle here. So the side opposite 30 degrees is going to be the x component of the weight. And we know that that component is the hypotenuse 6g times sine 30. Okay, so that's this component, this here 6g sine. I'm also showing it here. So we know that by Newton's second law, that's equal to the mass, which is 6 kilograms, times the x component of the acceleration. Well, the x component of the acceleration is just the acceleration, so we can drop this subscript x. This acceleration has no component in the y direction that is perpendicular to this incline. Okay, so here we have an equation in two unknowns. Now let's look at the 2 kilogram force, or the 2 kilogram mass. Downwards is positive for this, so the resultant force on it is 2g minus t. And by Newton's second law, that's equal to its mass, which is 2, by its acceleration, which is a. So we solve between the two equations. If you simply add the left hand sides together, the t's will cancel. We have minus 3g plus 2g is minus 1g, and here we have 8a. So we see that a is minus 18g. So the minus sign tells us that the system actually moves backwards, moves opposite to the assigned direction. We could have quickly arrived at this fact by looking at the resultant force along the string for the entire system. Okay, so we know that the x component of the weight is 6g sine 30, which is 3g. So this here is 3g. So if we take the resultant force along the string, we have 3g this way, but we have only 2g down this way. Of course, the internal forces are the two t's, and they cancel out. Also, we have an external force on the string that's perpendicular to the string. That's the force due to the pulley. Well, that has no component along the string, so we forget about those forces. We're only looking at the resultant force along the string. So we have 3g here. Say if we take this direction down, the incline is positive. Minus 2g. Okay, not to be confused with the direction of our x-axis here. It's a separate idea. So we see we have a net force, a resultant force of 1g in this direction. So 1g is the resultant force on the system, and it's in this direction along the string, anti-clockwise. So by Newton's second law, that's the mass of the system. Now the system consists of the two masses, 6 plus 2, and the string, but the string has no mass, so 6 and 2 is 8. And we multiply that by the acceleration, and you can see that a is 18g along this direction now. Finally, we can get t. So if I take upwards as positive for the 2 kilogram mass, that's the direction of the resultant force or the acceleration. The resultant force is t minus 2g. By Newton's second law, that's the mass, which is 2, by the acceleration, which is 18g upwards. So we get t equals 2¼ g newtons. In this problem, we have two identical particles, A and B. A rests on a rough incline. We know the angle of the incline, given by tan alpha equals 5/12, And we know the coefficient of friction between A and this incline. The system is released from rest, and we want to find the speed with which B strikes the ground. So it appears that B moves down. Now suppose we did not know the direction of motion of this system. Okay, the system is released from rest. Let's suppose that we just assume that B moved up and this particle here, A, moves down. Well, we've got friction in this problem, so the friction force on A would oppose its motion, so the friction force would have to be in this direction. So the configuration of forces is going to look different depending on which direction A and B move in. Okay, so I'm just filling out some of the forces. We have T up, the incline acting on A, and we will have a friction force, assuming that A is moving down the plane. This is the actual reverse of what really goes on. But if we were to, follow through all of this, we would get a negative value for A, telling us that we should reverse the direction. And it would be a mistake just to get the magnitude of A, because the reason that is wrong, of course, is this configuration will change when the system moves the other way. So let's go back to the actual correct motion of the system, which is given to us in the question in this situation. So the friction force is not pointing up this incline, it's pointing down the incline. Now, R is the force on A due to it being in contact with this wedge. String tension is the same throughout the string. And weight of B is mg. Okay, let's look at the resultant force on A. So, again, we consider two directions, or x and y directions. X is, the positive x-axis is up the incline. That's the direction of the resultant force, or the acceleration A. So like before, we're going to consider the x and y components of the resultant force. So to get the x component of the resultant force, we sum the x components of the four constituent forces that act on A. Well, we can see that vector r has no x component. It's entirely in the y direction. However, vector t does, and it's in the positive x direction. And F, the friction force, is in the negative x direction. Now what is F? Well, F is related to R. F is proportional to R. F is the maximum friction force that's acting, because A is either on the verge of moving or it's already moving. We'll just say that, okay, the system starts from rest, but we're assuming that it's just about to move, so the maximum friction force is acting. Okay, so more accurately, we have this force here is F max, and that's the coefficient of friction times R, where mu is a half, so we have a half of R. Now we need to find out what R is. Well, that's where we have to consider the y components of the forces. So I'll just write down F sub y here. So alpha is the same as this angle here, as we've seen before. So we want the y component of the weight, which is mg times cos of alpha. The y component is adjacent to alpha. Now F max has no y component and T has no y component. So let's get the y component of the resultant force. So we sum the y components of the four forces. Well, we have plus R, it's in the positive y direction, and we've minus mg cos alpha. And that's got to equal 0, because we've no acceleration in the y direction. So this would be mass times the y component of the acceleration, but the y component of the acceleration is 0. So we get 0 here. So in other words, we can just say that R is equal to mg cos alpha. So from now on, we just say that the vertical components balance each other. So this has the same magnitude as this. Now we know what alpha is. Well, tan alpha is 5 over 12, so the hypotenuse here is 13. So cos alpha is 12 over 13. So knowing what R is, we can get the maximum friction force. We get half of 12/13 mg, which is 6/13 mg. Okay, so now we can get back to the x component of the resultant force. So it's T minus friction force. And not only that, but we can see that the weight has a component in the x direction. That's along the incline. And this component is opposite alpha in this right angle triangle, so we multiply the hypotenuse mg by sine alpha. Okay, so it's in the negative x direction, mg sine alpha, where sine alpha is 5/13. Alright, so we simplify to this, and by Newton's second law, that's equal to the mass of A, which is m, times the acceleration of A, which we're calling little a. Now let's get to the force on B. Well, that's quite easy. The resultant force on B is mg down minus t up equals its mass, which is m, times its acceleration, which is a. We don't have to worry about x and y directions here. There's only one direction, and downwards is positive. So we have two equations and two unknowns. We have 13/13 mg minus 11/13. It's 2/13 mg. Adding the right hand side, we get 2ma. M's cancel, so we can see that the acceleration doesn't depend on the mass of both particles. So A comes out to be positive, so the assigned direction is correct. As I said before, if this had come out to be negative, well, the correct answer would not be got by making this positive, but we would have to redo the problem, and the friction force would be in a different position, so we get a very different answer. Okay, as for the speed of B just before it hits the ground, B is originally at rest, or it's just on the verge of moving. So its initial speed is 0. We have its acceleration. The distance that it needs to cover is 1 meter. So just before it hits the ground, it has traveled a distance of 1 meter. Okay, so we plug everything into this formula to get root 2g over 13 meters per second. Next, we want how far A will travel after B strikes the ground. So we've got to imagine that B has just reached the ground. The instant before B strikes the ground, well, A will obviously have moved up a certain distance. So A will actually have moved up 1 meter. The speed of A just before B strikes the ground will be the same as B, of course. The speeds of both particles are the same. Well, at least before B strikes the ground. So here's the speed of A just before B strikes the ground. So that's the initial speed. Now, to find out how far A will travel after this instant, we need to know what the acceleration of A is. So we need to know what the forces on A are. Well, the string goes slack, so there's no force on A due to the string after B strikes the ground. The two forces acting on A will be its weight, of course, mg, and the friction force, because it will want to keep moving in this direction. It has inertia, but friction will oppose it, and friction opposes motion, so the friction force will be pointing down this incline. So we saw what the friction force is. If it's on the verge of moving or moving, the maximum friction force acting is mu r, and that was 6/13 mg for this mass. So there are just two forces acting on it after B strikes the ground. Okay, the string becomes slack. So its initial speed is this, the same as the speed of B just before it strikes the ground. So these two forces will act to decelerate the mass. By the way, I forgot, of course, that we still have this force acting on the mass, but the vertical components will cancel out to 0. So when we're getting the resultant force, we only need to look at the horizontal components of these three forces. So the resultant force F is going to be minus 6/13 mg, minus mg sine alpha that we saw before. Sine alpha is 513. So here's the resultant force. The vertical components cancel out. Mg cos alpha is equal to r, so they cancel out. Of course, they don't contribute to that. So that's the resultant force. That's minus 11/13 mg, and by Newton's second law, that's equal to mass times acceleration. So now we have our A. It's different from before, of course. You can see it doesn't depend on the mass. So A is minus 11/13 g. So it's negative. So the acceleration vector is pointing in the negative x direction. That's down the incline. So what do we want in this problem? Well, we want the final velocity to be 0. And we want to calculate what s is, the distance travelled, till the mass stops. So here's our formula. A is negative. Since the thing slows down, it goes from this initial speed root 2g over 13 to 0. Multiply above and below by 13, divide above and below by g. S has to come out to be positive, of course, because we're moving in the positive x direction. So the displacement vector is positive. It's plus 1/11 of a meter.